Hey, this video has the solution for 2015 AB free response question number 4. This is a differential equation. You see a slope field thing happening here. So let's see what we got. On the axes provided, sketch a slope field for the given differential equation at the 6 points indicated. That is an easy thing to do, my friends. You just have to be careful. Okay, so this, let's see, I guess I'll start here at the top. So this is the point 0, 2. If I plug 0, I'm going to make a little chart here. 0, 2, these are my points. This is the point 0, 1 right here. This is negative 1, 0, negative 1. This is 1, 2. 1, 1. This is so easy, I just want to make sure I do not make any mistakes here because these are easy points. 1, negative 1. Okay, so how do you find the slopes at these? You just plug those, the x and the y, into your differential equation, right? dy dx is equal to do that to x and y. So multiply the x by 2, that's 0 minus y, so this is negative 2. And then 0, 1, that's just negative 1. So it looks like this, when the x is 0, it just flips the sign of the y coordinate, right? And then the slope's 1. So negative 2, negative 1, 1. Here, multiply the x coordinate by 2 and then subtract the y coordinate. So 2 times x minus 2, that's 0. 2 times, that's 2 minus 1 is 1. And then 2 minus negative 1 is 3. So those are my slopes. All right, let's just draw them in now. So I just draw a little line segment that has approximately this slope. So slope of negative 2 is about like this. Slope of negative 1, and 1, those are like 45-degree angles, right? And slope of 1. Slope of 0. Slope of 1, slope of 3. So how close do these have to be, you might be wondering, to get credit for them? Well, you just have to make sure that things that are supposed to be steeper than other things look like they're steeper, and slopes of 1, slopes of 0. You do your best, but they're going to be a little, nobody's going to be getting out their protractor here to measure your slopes. Okay. Find the second derivative in terms of x and y and determine the concavity of all solutions for the given differential equation in quadrant 2. Let's just do this first and then we'll come back and think about that. So how do I find the second derivative? You take the derivative of this, right? So the second, when I take the derivative of this, I get that. Right, the derivative of the first derivative is the second derivative. When I take the derivative of 2x, I get 2. When I take the derivative of y, I get dy dx. Right, the derivative of y is, the derivative of x is 1, but the derivative of y is dy dx. Now they said to find it in terms of x and y, and this is now in terms of, it's in terms of dy dx, so I can't leave it like this. But I can very, very easily just substitute. I know what dy dx is. It's this. So just substitute that, 2x minus y. You can distribute the minus sign if you want to, but there's really no reason to do that. Okay, so that's done. I've got that. Now what about this? Determine the concavity of all solution curves for the given differential equation in quadrant 2. So what's up with quadrant 2? In quadrant 2, x is negative and y is positive. So if x is negative and y is positive, that means that 2x minus y is negative. And if this is a negative number, then subtracting a negative number, we're always going to be adding something to positive 2. So 2 minus a negative number is positive. So if this second derivative is positive, then that means that everything is concave up. So a little reasoning there, not too tricky. You just got to think about what you know and do the best you can and see if you can get a good explanation for whatever it is you're trying to explain. For part C, let y equal f of x be the particular solution. That means we're going to solve this. Oh, no, we're not. Just kidding. But that would be if we were going to solve this. This is actually not one that you can separate, so we don't know how to solve that. So with the initial condition, f of 2 equals 3. So that goes through the point 2, 3. We don't even have that on our slope field here, so we couldn't do a sketch or anything like that. But they're not asking us to do that. Does f have a relative minimum, maximum, or neither at x equals 2? How are we going to do that? Well, to figure out if something has a minimum or maximum, we can figure out what is the first derivative and what's the second derivative. So what's the dy dx? I'm going to do this little notation where you do a line and then at the point 2, 3. That just means plug in 2, 3. It's a way of writing that. You can write that however you want, but I like that notation. So what's dy dx at the point 2, 3? Well, the slope at the point 2, 3, 2, plug in there, minus 3 is equal to 1. Right? So do we have a maximum, minimum, or neither? That's going to be neither, maximum or minimum. Because if you were going to have a maximum or minimum, you would have to have a slope of 0. Now, if I did get a slope of 0, then I would also check, since we found the second derivative here, I would check the second derivative also to see if it was positive or negative. As if you have a slope of 0, if your first derivative is 0 and it's concave up, that's got to be a minimum. If your first derivative is 0 and it's concave down, then it must be a maximum there. But I didn't have to do that because I didn't even get a slope of 0. All right. Last part, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. How would you do that? Well, let's think about what we know. If this is going to be a solution to the differential equation, then when I take the derivative of this, I have to get this. Right? If I take the derivative of this, which would just be dy dx, derivative of y is dy dx, the derivative of a number times x is just that number, and then the b, that's just a constant, so that goes away. So slope equals m, of course that makes sense because that's a line in slope-intercept form, right? So dy dx would just be m, but I also know that dy dx has to be this, right? So that means m is equal to 2x minus y. And that means that y, if I just rearrange, if this has to be true, y equals 2x minus m. So if you can see, like the slope, the equation is actually taking this form right here. So this right here, that has to be the slope, and then minus m, the opposite of that number, that has to be the intercept. So m must be 2, and then here's that intercept. The plus b looks like it's actually just minus m, so b is equal to negative 2. right? And then there's a thing that we need to know how to do where we don't need to do it here as part of our answer here, but we can do it just to kind of check our work, where we like just confirm that something is a solution to a differential equation. So here, my I'll do it up here. My differential equation, differential equation, differential equation, differential equation, differential equation. I said it 5 times. Not that fast, but I did it. So dy dx, what we're doing is we're checking to see if y equals 2x minus 2. That's what I'm claiming the m and the b are, based on my little bit of work here. To check to see if this is a solution to this. How do you do that? Well, you find the derivative of this, and then you replace everything here. So basically just like substitute things in. So here, dy dx, the slope of this is 2. So to check to see if this is a solution, everywhere where I see dy dx, I'm going to put in 2, and everywhere where I see a y, I'm going to put in this, and I'm going to check to see if it works. So dy dx would be 2, and then 2 times x minus y is equal to 2x minus 2, and then the 2x's would cancel out. Minus 2 is 2, so bingo, it checked out. We didn't actually have to do that to justify this, but I just wanted to show you what that process looks like. You want to check to see if something's a solution, just find the derivative and then plug in that everywhere where you see dy dx, or plug in this everywhere you see a y.